Good morning, everyone. So I would like to start by thanking the sponsors of the European Commission and the Marie Curie Actions project. This is the project number. And so the urinary tract infections, right? So it can affect any part of the urinary tract system. Specifically, the kidneys cause pyelonephritis. In the urethra, it takes urethritis, bladder, cystitis. And unfortunately, there is 56% infection incident for females, and that's 30 times more than men. So in UTIs affect more than 150 million people globally per year, and that's more than 4 million cases in EU, out of which 20 to 30% are preventable. And of course, that costs a bit of money. That's 1.6 billion US dollars annually. Now, if this disease is left untreated, then it can lead to sepsis, septic shock, and eventually death. And the current diagnosis protocol starts with the dipstick test, which takes 1 to 2 minutes. It's quite fast, but it's non-specific. It doesn't tell us how much and what bacteria cause infection. Now, the standard for these cases is the culture of the pathogen in a blood agar plate, and that's a bit longer, 24 to 72 hours, but tells us how much and what bacteria cause the infection. And so during this time, what's happening? Broad-spectrum antibiotics are being administered, and these often are unnecessary or inappropriate. They contribute to antimicrobial resistance, and this has been the same for the last 10 years. So an alternative approach to this diagnosis is gas phase detection. And there's been some work on that by using liquid cultures, where they take the headspace of the gases being released from bacterial growth, and then passing that on to GCMS and IMS, big machines that are very good. And specifically the E. coli, this is a bacterium, that is the dominant infection caused in UTIs, and is caused more than 50% of the hospital cases. For this bacterium, they found that it releases gases during growth, ethanol, acetone, ammonia, hydrogen sulfide, and more. And so this technique is specific for identification. It's very, very sensitive, detecting very low concentrations of gases being released from bacterial growth, but it's slow. And it's big and not practical, expensive, and at the same time is not of the current standard of blood agar plates cultures, in the liquid cultures. And so here we're proposing a new different technique that is taking the blood agar plate as it is, the gold standard, and culturing the pathogen in there, but using electronic gas sensor in real time connected to a PC. Unfortunately, this is measuring only the total VOC measurement, and it's lower sensitive than the GCMS and other methods, but it's real-time data, it's small, cheap, and it's in the standard of the blood agar plate. So this is exactly what we've done. We've taken commercial gas sensors, BME688, some electronics with SD card for data logging, and we put everything inside an incubator at 37 degrees. It's connected in real time to PC, so we can see the graphs in real time. And all the sensors are on top of these Petri dishes, where at the bottom we have blood agar, and in the blood agar we have E. coli type strain ATCC 25922. Okay? And so these are the results. And what we're measuring the change in resistance of the gas sensor. And that change in resistance is caused by the gases being released from bacterial growth. When the sensor detects gases, the resistance drops. So here we see initially that we have a bit of drift as the sensor adapts to the new environment. And we have some stability here, equilibrium. And then we have some change in slope here. And this is caused by the gases being detected from bacterial growth. So this change here tells us there's some bacterial growth happening. Moving on, there's a bit of, again, another equilibrium here, and then a larger change in slope, signifying, again, bacterial growth and gases being released, until, of course, the sensor saturates. And here we see the Petri dish after the 12 hours where we have a change in color. Now, as engineers, we don't like this graph, do we? I mean, look at it, it's messy, it's super noisy. How can we work with this? Obviously, by eye, we can tell there's something happening. We want to automate this process, have an algorithm doing that for us. And so to do that, we want to get rid of all this noise, which is basically a measurement artifact. And we want to do that such that we can apply change point detection technique to this data. Okay? And so to do that, get all of this red noise, we start by taking the envelope of the signal. Taking the envelope and then smoothing it. Now, interestingly, if you pay attention here, I don't know if we can see far at the back, but it's little bit tiny changes in the slope of that smooth signal. Which means if we do a piecewise linear fit, I don't know if you can see better now, there's many, many more changes. And that's not good. Because for change point detection, it can detect all these changes. It's a mess. We cannot really get around of this and be able to identify what's happening, identify the two main changes in slope from bacterial growth. And so at this point, we need to do something. After even smoothing, there's little changes that can affect the calculations. And so we do something counterintuitive. We're adding noise. And we're adding Gaussian noise with mean zero and standard deviation 5,000. And that's because the change point detection model was built assuming Gaussian noise. And so by doing that, we can mask all these little tiny changes. And therefore, from that, we can have our change point detection directly on this data now. And the model is scanning the data. And during this scan, is looking for changes in slope. And doing that, it gets this continuous piecewise linear fit better than before, and much fewer changes being detected. Of course, we have many of them again, and so what we do next in the algorithm is to select only those with negative slope change. And that's because this is one big change that we've seen before, and another one big change, and both of them bend down, meaning that the resistance drops because of the bacterial raising gases. And so we select the negative change slope, and out of those that are negative change slope, we select the major ones. And this is what we're left with. Exactly what we want. The two big changes. Of course, you have two lines, but either of them will work. Okay? And of course, we do the same algorithm for the rest of the data. So we start with 0, and you can see here there's no change in slope, only a bit of drift, and that's expected from sensors. There is no bacterial growth in the culture dish, but the rest 3, with increasing concentration of bacteria, that's colony forming unit per ml, we see changes in slope, 2 major change points as before, and the color of the Petri dish changes. Importantly here to notice is that we cannot see much difference between the culture dishes, even after 12 hours, but we can smell difference between these two a lot earlier than the 12 hours. Okay, we cannot see change, but we can smell change. And so we apply the same algorithm as before, envelope, smoothing, adding the Gaussian noise, and then change point detection. We get the linear fit. And from that, we can detect the changes as before, and then select the ones with the negative slope and the 2 major ones. We'll have exactly the same result. We'll have 4 here, that's fine, because either of them would do. Okay? Now, if the algorithm is so good, we want to automate this process. Do we actually need to do any filtering? Do we actually need to remove the initial noise? Well, in fact, the algorithm is so good, and it works on raw data. No envelope, no smoothing, directly taking the raw data, adding Gaussian noise, and do the fitting. And again, it works. We detect the changes, select the ones with negative slope change, and it works on all data. Again, raw data, no envelope, no smoothing, detect the changes, select the major ones, and that's it. By the way, this is the same threshold for all of them. Same algorithm for different concentrations. And so from this piece of information, what we can do, how does this come back to UTI detection? It comes back to the fact that we can get the time point change for different concentrations. And for that, we can feed a model and be able to predict what the concentration of bacteria is based on the time that we detect the change. And so we present a cheaper, faster, and smaller method for detecting UTI. And we do change point detection on raw data. And the message is, the higher the bacterial concentration, the faster the detection and quantification. Thank you very much.